let's take a look at this band voltage detector. This is one of these things that when you hold it up to a live connection, it lights up at the tip. And you think, well, hold on, they're not banned, you can still get them. Well, that particular one, oh, this is very flickery. See, that's one of the problems with the safe replacements, is they're not that safe. Oh, that is not a good one. But anyway, the reason that this particular type has been banned is because the first ones of these had metal bodies. And it meant you got a really good battery connection, but it also meant that when you were poking around in electrical panels holding the end of the metal tool, the rest of it, the metal body, was potentially going to touch live contacts in that panel if you were careless and give you a shock. And that's why they banned it. However, let's open up and take a look at what's inside. I shall tip out the batteries. This is ancient. This is really old. And I've probably had it apart. It's supposed to have a little pip across the end like that, but this has been destroyed in the toolbox. Is this going to come off? I don't think it's going to come off too easily. Let's grab it with pliers and try and get it off this way. Oh, that does not want to come out. That does not want to come out at all. I may have to pause while I try and extract this from here. That is super strong. I'm looking inside. I don't want to damage the circuit board because I want to reverse engineer the circuit board for our entertainment. Hold on. Oh, there it is. There it is. So for reliability, it's got a wire folded. Well, I'll show you. I'll take pictures of this so you can see it up close. Yeah, that's what I'll do. But the connection into the body, this metal body, is literally a wire folded up the side and connected on. And that's the, well, it's one connection. Is it the positive end? And, well, no, the positive end is coming down to here. That must be the negative end up the other end. Oh, let's get it out. Let's grab it with the pliers again, very carefully, and whip it. There's half a circuit board. That's not a good start. That's a very bad start. It did not like that at all. I feel like I've... Oh, it's ceramic. Right, okay, tell you what, one moment please. I'll just take a picture and we'll take a much closer look at this. It turns out that cracking that ceramic circuit board might have been a good thing, because I just went right to town on it, took all the surface mount components off, and found that there were hidden printed resistors underneath the integrated circuit. And see how I've cracked the ceramic? I think the designer also used a sledgehammer to crack a nut here. It's a very complex design. Let me zoom down a little bit closer so you can see this. So this is the circuit board cracked before I take the components off it. This is afterwards. This component here, the cryptically named HC14, is most likely a 7-4 HC14, which is a CMOS version of a TTL chip. There's a dual diode package, which I took it off and thought, is that a dual diode? And I just stuck it in the component tester. The component tester identified it incorrectly as a transistor and gave a gain value. I'm not sure how that worked. This, however, is a transistor. There's a couple of capacitors, filter capacitor cross supply, timing capacitor and filter capacitor for detecting the AC mains. Right, tell you what, let's go straight to the circuit board. Oh, this is the only resistor I couldn't measure in circuit, because all these other printed carbon resistors, I was able to find adjacent pads and get a resistance reading. They're all very high value. This one, because it had cracked, I couldn't get a solid reading in that. But I know from its position in the circuit, I'm going to guess something like 100 megohm. It's going to be super high. Let's take a look at their schematic. Anything else to look at here? Nothing really. Okay. Very expensive circuit board to make. Strange. I'll show you the other one afterwards, which is not an expensive circuit board to make. Incidentally, this is the dodgy one that's supposed to ban because the metal. I've reincarnated it with the circuit. You can see it flashing there. It doesn't flash in real life. You're seeing the 50 hertz pulsing because I've put the other circuit in it. Anyway, we have rather oddly a 10k resistor. I'll mark that in 10k, being used as an antenna here. So initially we've got the 3-volt supply from the AAA cells. We've got a 1 nanofarad capacitor across this. That's not a very high value, but the whole current of the circuit is tiny, so it's an ample for the filtering. And we've got that little chip which contains 1, 2, 3, 4, 5, 6 inverter gates. And those inverters are Schmitt trigger inverters, which means that as the voltage into them rises, the output will suddenly click on And then as the voltage falls again, it will suddenly click off. There's a sort of hysteresis and a very decisive on-off switching. This is useful. They're incredibly useful components. So the resistor here is just basically, they've cut the lead off it, and it's used basically to fill the tip of this probe with conductive material in the form of the resistor. I suppose it was the cheapest way of doing it. And it's self-centered in the probe and gave a sort of large area for the pickup. There is this massively high-value pull-down resistor to allow the stray pickup field from the tip of the probe to actually influence the input of this gate, because if it was just left floating, it might be too sensitive. This has been used to tune it down and actually give it a certain threshold before it will detect. Once it detects the AC coupled signal from a live wire, it goes via this 10 megohm resistor and to the input of the gate. These gates are super sensitive, and then the output of that gate will start pulsing up and down in time with the sort of mains alternating current. That is then filtered via this capacitor, so only pulses will affect the output, which is unnecessary. And there's a 10 megohm resistor pulling the input to this logic gate high to keep it in a stable state. That then effectively, because this one's pulsing via the capacitor, this output starts pulsing sharp spikes. The output then goes through what's called a charge pump. This diode here only lets the current flow in one direction. And because the output of this is effectively pulsing high, that uses those pulses via the diode to start charging up this capacitor. And after a certain time delay, determined by this resistor, the input to that gate will go to a level that it changes state. So this is used just to introduce a time delay to stop spurious glitching. And this discharge resistor here just makes sure that once the pulse has stopped, it brings that down again, and it basically goes back to its standby state, waiting for more pulses. The output of that then goes to this gate, which then, because it's inverted, goes through another inverting gate to then drive the transistor, which then switches the LED on via, what was that resistor? 21 ohm, a 21 ohm resistor. So let's recap very quickly. The input of this gate is being pulled low by this resistor, so the output is high, but nothing happens because there's this capacitor to block the signal. When that starts, detects the signal, it starts pulsing the output the opposite polarity, and then current can flow through a capacitor. This is normally being pulled high, which means the output is normally low, which means no current flows through that diode. When this starts pulsing, that then positive pulses then go through this diode and charge up the capacitor. The capacitor is normally, the input to this gate is normally pulled low, which means the output would be high. And when this starts pulsing, it reaches that threshold, that then goes low, which then gets inverted again, goes high, turns on the transistor, switches the LED. These gates can sink a bit of current, not a lot of current, but it would have been enough theoretically to drive the LED. They could also have used those spare gates theoretically. You can give your opinions on this. In a cluster like this, this is just a thought, to actually beef it up a little bit. Well, that's showing that as a diode, that's not a diode. And maybe get rid of the transistor. But anyway, the other circuit that we got, the other probe is a lot simpler, because this is just ridiculously complicated. The other circuit has 3 transistors. One set is a high gain input, that's this one, and then the other 2 is a Darlington switching the LED. And I'll show you the schematic for that. I mean, that's basically 1 resistor and 3 cheap transistors. The schematic is much simpler. Much simpler. This is the one you'd want to build for fun. It doesn't really matter, it's fine, it'll light when you put it near a live wire. We've got the AAA cells, 2 of them, giving the 3 volt supply. The base input is literally a spring to give it a sort of wider electrode with a stiff wire up in the middle of it. They're just looking for a fairly large sort of, basically, well, they've basically got a spiral like that just inside the probe tip, just to give it a sort of largish detection area. It increases effectively capacitive coupling. So it goes to the input of this C3199 transistor, and that has a 3 megohm resistor, pulling the base of this Darlington pair down to the 0 volt rail to keep it off. Quite a high value because this has to override it. that buffers the detected signal up. It effectively pulls that high, turns on the Darlington, and the LED is in series with the Darlington, but because the whole signal is very low in the first place, and even with the gain, there's not going to be a huge amount of current, it just drives the LED directly. Also, you've got the 3 volt minus a slight drop across the Darlington. But that's it. It's very, very simple. The other circuit is very dignified. It's very professional looking, but just a very expensive, and the ceramic circuit board and everything, and the integrated circuit and everything. It just made it very complicated. But there we have it. Banned because of the metal case, but actually contained quite a sophisticated bit of circuitry. The power tracer, live wire detection probe. Very interesting. Turns out it was well worth taking apart. Very interesting circuitry.